over here, and that's the state vector xt, which is basically the same thing that I have over there on the right hand side. So I'm not saying anything different, it's the same thing, except my x's go from here to there arbitrarily, and I'm sorry about that. In the text, this is always a vector, and that's always the transform or a matrix, but here my writing is not so good. Okay. Anyway, so this is actually should be small x of t. Okay. Now, what Lyapunov was trying to do was to say, when is a system considered to be stable? So he started out by saying, okay, let's assume that the ideal equilibrium state is x equals 0. So I want to say x of t equals 0, the vector 0. And in this case, let's say the bottom part of this dish is the 0 point. Okay, we want that to be stable. Okay, and so, okay, we can always choose that to be the case. Then what we want to do is we want to understand the modeling of how the system works over time. How does it actually work? And we're going to just write it as this. We're going to say x dot, this is the vector, is going to be some function of x. Okay, we don't know what function of x is, and if you want to be more precise, we'd say some function of x of t. The t is implicit in this whole thing. Okay, remember, this is not the same as that. Over there, x dot is going to be ax plus bu plus fw. There's some disturbance, there's some command, and then there's the a is a matrix, right? Here we don't have a matrix. We're saying it's some arbitrary function of time, okay, because it's f of x of t, and it is going to be, could be nonlinear, it could be anything, we don't really care, but it's telling us something, and we're going to get what's called the trajectory. The trajectory is essentially the path taken. So x, this is actually x, the position over here is x, and the trajectory is, what you can think of it intuitively is what is the path taken by the ball. So if you take the ball and you kind of flip it like so, it's going to go round and round, okay, like in a spiral, and then eventually it's going to go to the bottom and it's going to stop there because you dissipated all the initial potential energy as sound and heat. Okay, so it's gone away, and so it goes to the bottom, and then it, it stops there. Okay, and the second thing is that we can see in the system that when it's at 0 and nothing is happening, it's going to stay there. So f of 0 is going to be 0. So let's assume that's the case, and we want to study those systems where if you're at equilibrium, the system doesn't do anything, it just stays there. Okay, so the equilibrium position is a stable position. That's what we're saying over here. Okay, this is like a cone like this. Okay, obviously we can also define upside down cone to have this property which precisely balanced at 0 as long as there's no disturbance. That's also, in this sense, it's stable. Okay, it's also stable because certainly it satisfies f of 0 equal to 0, and we can define x as a function of this. But it's stable at this point. Okay, but is it stable in the sense of Lyapunov? No. Okay, to be stable in the sense of Lyapunov, what we do is this. We say that we can define some region around this, okay, in space around the equilibrium point, such that as long as the disturbances, as long as the initial position which corresponds to disturbance is bounded by some value, okay, then the output of the system is also going to be bounded. Okay, so let's say that my initial state over here is this, okay, on the edge of the bowl. I'm saying that if I have this on the edge of the bowl, and then I can say that the bound is the whole bowl, okay, as long as it's somewhere in the bowl, eventually it's going to drop down to the bottom, okay, but I don't need to. I could have what's called a limit cycle. It's fine for this ball, for this thing to come like a little bit down here and then kind of go like this round and round forever. Okay, that's acceptable as well because it's bounded in its space by some value. Okay, so what Lyapunov said was that intuitively or mathematically we define a system to be stable. Intuitively it is stable if it's stable at x equal to 0, so it has to be at the equilibrium point. Okay, if for all epsilon, which is your greater than 0, there exists delta greater than 0, such that if this norm, the second norm, x 0 is less than equal to is less than delta, then for all t, norm x t less than epsilon, where norm x is just going to be square root of x t x. So x is this column vector, xt is this row vector, this is xt, this is going to be x. So the row vector multiplied by column vector is just going to be x1 squared plus x2 squared plus, and so the square root of xtx is going to be this square root, and this of course is the Euclidean distance of the point in state space from the 0 point, which is the 0 point over here. We define this to be 0. Okay, our z-axis actually goes up right through the middle of the bowl. Okay, and so what you can say is that, let's say that we were to have the initial point be sort of over here, okay, which is sort of outside the bowl. We hold the marble outside the bowl and it kind of drops and this kind of rolls away. Is this system stable? Okay, in the sense of Lyapunov. Okay, anybody want to answer that? No, but let's look at this definition over here, okay? That's right. So this is not stable because the definition is that for all epsilon greater than 0, okay, there exists a delta. Wait a minute. Wait a minute. It's the other way around, isn't it? So I should have, for, yeah, it should be for xt is less than, for, okay, so for all, let me see. So I want to make sure that as long as its input is bounded by epsilon, the output is bounded by delta. So, right, so this is wrong. Oops. I think I got these switched up. Okay, so, right, for every for all epsilon, I can define the output to be less than some delta. That exists or yeah. So I'm given this, and I'm going to make sure the output is less than this. So in this case, there exists some value is epsilon which is outside the bowl, okay, where it is not going to be less than delta. It's going to roll away, so you know it doesn't meet it. But if you say the system is confined to this, or it's an infinite bowl, then we'll say it's stable in the sense of Lyapunov. Okay, so we want this sort of space to be, there is this, if I confine it in the initial conditions, then it's going to be, it's not going to wander too far. Actually, I'm not, it can't be a for all there. Wait a minute, I better read this carefully. Because my understanding is that there is a definition of the input. Let's see, we have to confine the initial trajectory. So every real number epsilon, the x. Right, so I did have it right the first time. Okay. Let me see, for x and delta, okay. Let's see. For every real epsilon, right. So, okay, sorry. I'm getting old. Okay. So here is the thing. I want to make sure that for all t, xt is less than or equal to epsilon. So I want to bound the output. Okay. I want to bound the output for all time. So if I say I want to make sure that this value epsilon is not exceeded. Okay, so that's the challenge. Can you make sure that you never exceed epsilon? You say, okay, fine, I'm going to give you a delta. As long as you stay within this delta, life is going to be good. So it's like think of it as an adversary kind of thing. Okay, so the adversary comes and says, I'm going to pick an epsilon, which is this. Can you find me a delta? And you say, yeah, I found a delta. This delta is over here. It's the limit of the bowl. Okay, and as long as you stay within the bowl, you're going to be within epsilon. Okay, and that's why this works. Okay, so I did have it right in the beginning. So, so think of yourself as being, let's say, a process engineer, and there's the error tolerance. Okay, so the manager comes and says, we need to make sure that the chemical composition of this, biochemical thing is plus minus 1%. okay, of the ideal condition for some pharmaceutical. Okay, that's what you can think of. So you say, okay, that's my epsilon, 1%. I want to make sure that at the end of time I'm within 1% of the value. Then you say, okay, then you have to I have to guarantee that at the start of the process you're not too far away, so you're going to make sure that within delta of the operating range. Yes?
For every real number epsilon,
Right.
there exists another real number. So it's not that adjusted. So we should have the kind of delta that works for our system.
Right. So if
Cannot be adjusted. If it was reversed, it would say there exists delta epsilon. Then
see, the thing is, the adversary is saying, I want you to, I'm giving you epsilon. And then you say, okay, I'm going to find the corresponding delta for it. That's what you're saying.
but what
Yeah.
first for every,
Yeah.
then there exists,
Right.
so there exists delta, but it's not adversary.
So the thing is, think of it as this way. You can write this as delta epsilon. Okay, delta is a function of epsilon. So I'm giving you an epsilon, and you give me an epsilon, I'll give you back a delta as a function of epsilon. That's what I'm saying. That's why I said it's like an adversary. It's not adversary in the sense of being pathological. I'm going to find some, it's not a game theoretic adversary. This is more of a, if you give me the epsilon, I'll give you a delta that's a function of epsilon. So for all epsilon, there exists a delta function of epsilon such that if the input is less than this, I'm controlling the input, then the output will be less than the desired value that you give me. Okay, but that's the sense anyway. If you want me to confine it to this part of the space, then I'm going to request you to make the initial value confined to some other initial part of the space. And as long as that's true, we have Lyapunov stability, or stability in the sense of Lyapunov. Secondly, let me just finish. If we are going to get to the equilibrium point, then we call it asymptotically stable in the sense of Lyapunov. So not only are we going to keep it bounded within this range epsilon, we're also going to get to 0 eventually. Okay, yeah. Sorry.
In this system, do we consider any kind of disturbances?
So the F is going to encapsulate any other disturbances and so on. So F is very general. Okay.
So you are considering the fixed-length system.
All right, everything is F is basically arbitrary. Okay, I'm not basically telling you the modeling or anything. I'm just saying this is the definition of stability. Okay, we're trying to capture intuitively what is the meaning of stability.
Because if you don't have to consider the ideal situation, what makes the several position station ball.
Yes.
It's just the pendulum kind of motion.
Right.
And then that's in equilibrium.
That would be in equilibrium because you would say, I will say, okay, I'm going to place the ball over here. If there's no dissipation, then I'll say, well, delta equals epsilon. It's going to be frictionless and it's just going to stay confined in that space. So if you give me epsilon, I'll say delta is same as epsilon without any friction, right? Trajectory is going to be non-dissipated. Okay. Any other questions about this? Yes. Define trajectory. Trajectory is the official the official definition of trajectory is these elements x of t. The x of t is a function of time. Okay, x of t is defined to be the trajectory. There you go. It's a vector. It's the values taken by the state space variable over time. It's a trajectory.
So it's a history of vectors of x of t?
Yeah, history of the vector x of t. Yeah, I mean, it's the same as this, right? I mean, it's a function of time. Yeah. Okay, that's all right. Yeah, these epsilon delta things are kind of, they show up all over the place and you have to get them just right. So this is often called two stability or Lyapunov's second method, because Lyapunov in his paper had two methods, and the first method nobody uses and the second one is what we use. And so in this two stability approach, the second method, what we do is we have an auxiliary function and it's a scalar function. And the scalar function is some v of x of t, where x is a vector. And so of course V is going to be a function of time as well. Okay, so we interpret V as the energy at that time t. Okay, and what Lyapunov proved, and Lyapunov's theorem says that if we can think of the energy, if you think of the, if you can prove that the energy is always going down with respect to time, and the energy is 0, the minimum value at the equilibrium point when x is equal to 0, then basically we have a system that is stable. Okay, I mean that's kind of intuitive, right? So you take a system, and let's say we have a system where, like in the homework, the system where we have the energy defined to be the buffer contents of all the buffers in the network, right? So the more the stuff is in the buffers, the more energy there is. And this is, by the way, not just made up. If you remember from the beginning, when you talked about flow and effort and energy and power, we saw that buffers holding packets are in fact energy. Okay, that's the definition of energy in the computer network. So it's a very natural modeling to say that the energy in the system is this. What Lyapunov said was we want to have the following. We want V of 0 to be equal to 0. So we want the energy at the equilibrium point to be 0. Okay, that makes sense. Second, we want V of x greater than 0 if x is not equal to 0. So we want to make sure that at any other point other than the equilibrium point, the energy is non-zero. And the reason is because we don't want to have a bowl like so with a local minimum like this. Okay, actually we should go like that, right? If you had a bowl with a sort of a sinkhole over there, you might end up trapped over there rather than over there, and that's not nice, right? So we want to have what's often called global convexity. Okay, and global convexity means that no matter where we start, we're going to end up at the single unique point, the equilibrium point. And so there's a global convexity condition over here. So the third thing is that this is a technical point. We want Vx to be continuous, and then dV by dxi should all exist and should be continuous with respect to, so both it has continuous partial derivatives as well. So this is more of a technical condition for the proof. Both Vx should be continuous and dV by dx should be continuous. And then most importantly, dV by dt, not dV by dx, but dV by dt of x should be less than equal to 0 for all trajectories. Okay, then intuitively what we're saying is that no matter how the marble is rolling down this bowl over here, basically it's going to get to it's going to always lose energy. In our case, potential energy is what we care about, because 0 potential energy is the bottom point. So it always is going to lose potential energy. It's not going to, kind of go up again. Okay. Now obviously, purely potential energy here is not going to work. We need to look at the sum of potential plus kinetic, because if it goes down and then up again on the other side, it's gaining potential energy. So an auxiliary energy function that says only potential is not going to work for the system. But if you take the total energy, potential plus kinetic, then we will find that this is going to be true. Okay, and this again is a lot of sense. If you have energy, the energy is going to dissipate. And so obviously the end of, asymptotically we're going to get to a state where we are going to be having 0 energy, because the energy keeps going down. Now notice this is less than equal to 0. It is possible to have like a limit cycle, as I showed over here. We go round and round and round. We never drop down, where the energy is equal to 0. Okay, dV by dt is equal to 0. In which case we have, as I said, it's called a limit cycle. And then we'll say it's Lyapunov stable, but not asymptotically stable. However, if this is less than 0, then we're going to have something that is asymptotically stable, because we're going to always have the energy decrease over time. We're going to get down to 0. So to get to the homework question, what is it that we need to do in a computer network to make sure that the energy is always going to be decreasing? Well, what is the energy? Energy is the amount of buffers in the system. And so the controller, basically all it has to do is to ensure that whenever the packets in the buffer, serve them. Don't just let them sit there. Always serve packets waiting to be served. Don't just not serve them. And as long as you do that, that energy function is going to dissipate. Okay, and that's a very, very simple reason why we can say that all computer networks that are halfway reasonably built, where you say, okay, so there's a packet coming in, I'm not going to ignore it, I'm going to do something about it, is going to be Lyapunov stable. Okay, it's a pretty straightforward condition. Okay, the other thing you can add to it is to say, what about loops? So I'm serving it, but then I'm not getting. Loops can be thought of as being stable, but not asymptotically stable. Okay, because you aren't injecting any more packets into the system. And if you have time to live, then that becomes asymptotically stable, because at some point those are going to go away. So the intuitive notion of Lyapunov stability also allows us to determine what to do in a controller. So if you're building a real system, what you need to do then is to think about what energy function V can I use, and then just say, okay, what actions do I need to take to ensure that the V is always going to go down with time? And if you do that, basically you'll end up with a Lyapunov stable system. Okay. The biggest problem with these, with this kind of approach is that it's not always possible to find V. Yeah. Say that again. What is the first part?
One system at a time.
Yeah.
For example, when you have a mission message and it sends you back an email.
Yeah. Yeah.
Well, that server itself will be stable because it only takes that one
Yeah.
petition to care about.
That's right.
But then if you look at the whole internet, everybody just has
Right. It would be if you send for each message one message back, it would be stable but not asymptotically stable. But if each message you send to a mailing list of 10 people, then it would be asymptotically unstable, because then energy is going up with time. So I think the question you're asking is deeper than that. It says, what is the meaning of system, right? And the answer is, it's what you choose to study. Okay, if you say I'm going to look at just this one piece, sure. But then if you expand your scope, you get a different answer. So as you keep expanding your scope, you get different answers. Okay, and so there's no rule that says this is what your answer is. It's like, yeah. Okay. Any other questions? Okay, I'm going to now kind of start on the state space control part a little bit, and then I guess we'll continue with that next time in physical control. Spending a lot of time on Lyapunov stability, because in fact this is the one piece of control theory that might be very useful even in nonlinear systems, which is what we end up studying a lot. And it's a very nice intuitive concept, and in fact turns out to be relatively easy to apply. Okay, the theorem is easy to show, the method is easy to apply, so it's really nice. Okay, so we're going to jump back into LTI systems, and the LTI system using state space approach over here. And now I'm going to kind of change from the classical approach to the modern approach, what's called the modern approach. So the classical approach is basically is transfer functions, and where we look at the control system from the perspective of y equals 1 over 1 plus GDH u plus whatever something w. Okay, everything is based as the product of transfer functions, and it works whenever you have a single input single output system. Okay, but it has some problems, and let me tell you what the problems are. The first one is that it's only for single input single output system. Okay, if you have multiple inputs or multiple outputs, you can't really do it. The second one is that it doesn't really talk about internal state variables. Okay, so in other words, we can show that the output is going to be stable, the output is going to be bounded or stable or whatever, but we don't know whether the internal state variables are going to have that property or not. It's possible that the internal state variables are going to be unbounded, or even if they're bounded, they have wild oscillations, but the output is not. So from the perspective of classical control, we don't really care what the internal state is. You say, well, I don't really care. I just want to make sure the output looks okay. But in some cases, you do care. You do want to make sure that the internal state variables aren't, quote unquote, too large. And we'll quantify that later. The third problem is that you can only use the output measurement. measurement. Whereas in many cases, we actually have the ability to measure the internal state. Okay, what is a black box, or can be thought of as a black box of the plant, actually has some structure. We can actually measure it, and that measurement can help us make the system better, but classical control won't allow us to use it. It says, no, sorry, that's part of the plant. Even if you can measure it, I'm only going to measure Y, because we have this system over here. We have G, and we have this Y, and I'm only going to measure Y with my H, and that's what's going to be fed back into my controller D to go into the plant, right? So this is what's going to happen. What if I could measure G, and that was also available to me like so? Okay, classical control says, sorry, can't do that. Okay, but in modern control, we say, oh, wait a minute, we can use that information. If we have this additional path where the input can be, or maybe you can feed it back like this to D, or if you can use this, well, why not? Okay, and so modern control, state space control, allows us to do that. And the other thing is that it doesn't have any issue of power limits. In other words, the control action over here, U, is going to be essentially unlimited. We don't really have any limit on it. If you have error E, you're doing proportional control, the output is going to be KPE, may be very large. If K is large, if your loop gain is large, control action may be very large. But we can't control it, but it costs us something. It costs us some energy to do that control action, but we can't say that. We can't control that. Or I should say, we can't limit that. So for these reasons, around the 1950s, a bunch of people said, look, let's see if we can do better by using a different approach to control rather than using the classical transfer function approach. And that's what came up, and then they came up with what's called the state space control approach. And this is, again, using these equations over here and using the techniques of linear algebra, which essentially were not explored very well by control theorists until the 50s. So with the advent of linear algebra into the picture, we ended up with what's called modern approach to control. Modern approach is at this point sort of a misnomer. It's almost 60 years old, so it's hardly good idea to call it modern, but it's better to call, I think, transfer function approach or classical approach to state space approach, which is what I'll talk about here. So I'm going to just sketch the development of this briefly, and then we'll continue with this next time. We're going to start with that same equation over here, where we say the state over here evolves in some fashion, and the Y output is some function of the state. So that's the basic equation. And we're going to start with studying the zero input system, just to make things simple. And if you assume zero input, then we get back to this simple equation, x dot equals ax. Now what we did last time was, when we looked at this equation, x dot equals ax, was to look at the dependency on x0, and we did that by essentially taking the Laplace transform. But let's say we don't do that. Just for the sake of argument, we just see, let's stay in time domain for a moment and see what it's going to look like. We see that if we have the scalar, this is a vector over here, if you have scalar y dot equals ay, we know the solution of this is basically y equals, or let me just put this y equals ay. We know the solution is going to be y's of the form some constant c e to the minus at. Okay, so that's the scalar solution. So whenever you have a homogeneous differential equation like this, y dot equals ay, this looks, because, and the reason is because y dot over here is going to be obviously c a actually it's plus at c a e to the at, right? And so obviously y dot equals ay is going to work for any value c. It's going to be true. So in the same way, we kind of say, by analogy, we think that this solution is going to be looking like something like x equals some e to the at, okay, k, where k is some vector, okay, which is corresponding to this c over here. So this k is basically corresponding to this constant c over here, and that e to the at corresponds to this, and e to the at is actually the matrix exponential, okay, which is defined, as you know, as I plus AT and so on and so forth. So e to the AT, should just write this down, e to the AT equals I, oh, am I going over time? Okay, well, just a minute, I plus AT plus a square by 2 factorial, t square, etc. And if you take this definition over here and substitute it over here, and you do the actual, derivative of this step by step, you'll find that this actually is a valid solution where we've taken this matrix exponential. And the other thing we can do is we can set t equals 0. If t equals 0, then basically x 0, this is going to be 1, is going to be k. So then the general solution is going to be x equals x 0 e to the at. Okay? And by comparison with the previous one, we'll see that basically e to the at is nothing more than the inverse Laplace transform of what we saw earlier. I would say erased from here. But we can get these two ways of defining the same thing. So now the game is, how do you find e to the at? Because it's this fairly complex thing over here. And so next class I'll show you a couple of different ways of computing e to the at. And if you do that, then we can compute the time evolution of every component of the system space without, using just with this linear algebra over here. There's a typo in the text, by the way, on the last line of page 248. It says it's easy to see that ck equals x0. There shouldn't be a c, just k equals x0 is what I meant to say over there. So you should make that correction. And yeah, I think there are no other errors other than that. And then, okay, so we'll continue with this next time in digital control, and then that will be the end of control theory.